Hello from the European Micro Week 2018 in Madrid. In this application, I would like to show how to perform multi-channel signal analysis using our new RTP high-performance oscilloscope. As application example, I have a 77 GHz automotive radar link, and I analyze this with two receive antennas. So I downconvert the 77 GHz signal to an IF frequency using external mixers from Rode and Schwarz, and I do the analysis on the RTP. The analysis is simple. I measure the phase difference between the first and the second receiver, as well as the amplitude difference. If I, for example, change the distance, you see on the screen how the phase and the amplitude is changing. Now, the question is how we can do this. We can do this because we have a very high acquisition rate with our RTP, up to 1 million waveforms per second. In addition, we have a lot of hardware acceleration, and last but not least, we have a real-time de-embedding capability. Real-time means in that regards that all samples which are coming out of the AD converter are compensated in terms of S parameters, which are describing the signal path. And I would like to show you this briefly. So I have set up on the instrument, I have described the signal path in a way that I have my device under test here. Then I have three different blocks. The three different blocks are the mixers, the cable, and my adapter here. And each block is individually described in terms of S parameters. So for the mixer, I have the conversion loss, and the conversion loss under this condition is ranging from -15 to -20 dB. In combination with the cables, we also see, for example here, the complete conversion loss, the magnitude response. The main driver is here the conversion loss from the mixer, but we see the ripples, they are introduced due to the mismatch of cables, adapters, and the mixers. What the de-embedding in real time is giving me as a result, based on this curve, it's a very flat response. And just to give you an impression how good this is, I open the magnitude response curve, I apply small zooming, and then you see that based on this 15 to 20 dB of conversion loss, the algorithm, the real-time de-embedding, is correcting this in a very nice way that the losses are less than 0.5 dB. So how does this affect my measurement result? So if I enable this one, if you look at the two magnitude measurements, if you look at the spectrum, if I simply disable this for one channel, you see that the magnitude drops, the demodulated FMCW chirp has some uncertainty inside. So to summarize this with the RTP, with all the hardware functionality and hardware acceleration we have on board, we are able to measure, to demodulate chirps in higher frequencies. So in this example here, we do a 77 GHz automotive radar link measurement on a 8 GHz RTP oscilloscope.